We are in section 10.4, areas and lengths of polar coordinates. Area of a sector is A equals 1/2 r squared times theta, and the area of a polar region with polar equations r equals f of theta for theta between A and B is going to be A equals 1/2 times the integral from A to B of r squared d theta. The area of the region bounded by two polar curves is A equals 1/2 times the integral of f of theta squared minus g of theta squared d theta. And so they should look very similar to the ideas that we discussed back in chapter 6, but extending those upon what we're talking about right now, which is with polar coordinates. The first example says, find the area of the region that is bounded by the given curves that lies in a specific sector, and we have r equals cosine of theta for theta in between 0 and pi over 6. So setting up our integral and using what we have stated up above, we have the area is going to be the integral from, and we have from A to B of 1/2, and I'll put the 1/2 out in front, r squared d theta. And so for this problem, we have 1/2 times the integral from 0 to pi over 6 of r squared, and for us, r squared is going to be cosine of theta, so cosine squared theta, and then d theta, which we learned how to integrate back in chapter 7, and I'm going to go ahead and use that power reducing formula that we discussed back then, which is now going to be the integral from 0 to pi over 6, keeping that 1/2 out in front, and then cosine squared theta is equivalent to, and it's 1/2 times 1 plus cosine 2 theta d theta. And so you can pull out the 1/4 now. And integrating this, we're going to have the integral of 1 is just theta. And then the integral of cosine 2 theta is going to be positive 1/2 sine 2 theta. And we're going to evaluate this whole thing from theta equals 0 to pi over 6. And so for this, we would have 1/4 times pi over 6 plus 1/2 times sine of 2 times pi over 6 would be pi over 3 minus 1/4 times 0 plus, and then sine of 0 would just also be 0. And so this is going to simplify to 1/4 times pi over 6 plus 1/2 times, and sine of pi over 3 is equivalent to rad 3 over 2. And so from here, simplifying this a little bit more, we arrive at pi over 24 plus the square root of 3 over 16. And again, this is the area of that region that's bounded by the curve, and that's between the values of theta equals 0 and theta equals pi over 6. We have another example below that says sketch the curve and find the area it encloses, and we're dealing with r equals 1 minus sine theta. And so dealing with 1 minus sine theta equals r, the graph is given over here. And so we're going to be looking for the area that's enclosed by this curve. And so in order to do that, we know the area formula is going to be 1/2 times the integral from A to B of r squared d theta. And so if you notice, we start and stop in a certain spot because it's creating a circle with these polar coordinates. And so for this, we have it starting and stopping. I'm going to go ahead and use from 0 to 2 pi. So this is going to be 1/2 times the integral from 0 to 2 pi of r squared. And our r value here is 1 minus sine theta squared, and then d theta. So then multiplying this out, we have 1/2 the integral from 0 to 2 pi of 1 minus 2 sine theta plus sine squared theta d theta. And we can integrate all the terms except for this last one, and we're going to go ahead and use that power reducing formula like we did in the previous example. So this is going to be equivalent to 1/2 the integral from 0 to 2 pi of 1 minus 2 sine theta plus 1/2 times 1 minus cosine 2 theta d theta. And then distributing this 1/2, I'm able to combine some terms. And so we have 1/2 times the integral from 0 to 2 pi of, and we have 1 plus 1/2, so I'm going to rewrite that as 3 over 2, and then minus 2 sine theta minus 1/2 cosine 2 theta d theta. And so the 1/2 would stay there, and then integrating each term, we get 3 over 2 theta plus 2 cosine theta, since integrating sine of theta is going to become negative, and that would become 2 cosine theta, and then minus 1/4 sine 2 theta. And then we're going to evaluate this, and I'm out of room by evaluating from 0 to 2 pi. So substituting in 2 pi first, we have 1/2 times 3 over 2 times 2 pi plus 2 times cosine of 2 pi is 1 minus 1/4 times sine of 2 times 2 pi would be 0 minus 1/2, and substituting now in 0, we have 0 plus 2 times cosine of 0 is 1, and then minus 0 for sine, because sine of 0 would just be 0. And so this simplifies to, we can reduce those 2's, and we're going to have 1/2 times 3 pi plus 2 minus 1/2 times 2. And so again, distributing this, we end up with 3 pi over 2 plus 1 minus 1 would just be 3 pi over 2. The next example says find the area of the region enclosed by one loop of the curve, and the curve here r equals 2 sine of 5 theta. The graph of the polar equation r equals 2 sine 5 theta is given to the right. It does make a rose curve. It also says in only one loop, and right now this one currently has 5 loops, and so I only want to deal with one loop, so I'm going to go ahead and shade that one loop that we are going to deal with. Doesn't matter, they are all equal in terms of the area. And so looking at this, we're going to have the integral from 0 to, and we have to figure out where this curve comes back to that pole, so we'll talk about that. And we have 1/2 r squared d theta. And so for this problem, we're going to have 1/2 the integral, and we'll talk about where this region is bounded in just a moment. R is going to be 2 sine 5 theta, and we're going to square this d theta. And so noting that this first petal that we're dealing with here starts at 0, and sine of 5 times 0 would be sine of 0 or 0. So this would also come back to the pole or equals 0 when we have sine of pi, and so that means that theta would have to be pi over 5. And so simplifying this, we end up with 1/2 times, and then squaring both these terms, I'm going to have a 4, I'll pull that out in front also, times the integral from 0 to pi over 5 of sine squared 5 theta d theta. And so from here, simplifying this, we're going to have 2 times, and I need to use that power reducing formula again. So the integral from 0 to pi over 5 of 1/2 times 1 minus cosine of 2 times theta, but this time we don't just have theta, we have 5 theta, so 2 times 5 theta d theta. Simplifying this a little bit more, the 2 and the 1/2 would reduce, and so we just have the integral from 0 to pi over 5 of 1 minus cosine of 10 theta d theta. And so now integrating this, we get theta minus 1 over 10 sine of 10 theta, and we're going to evaluate this whole entire expression from theta equals 0 to pi over 5. And so by first substituting in pi over 5, we have pi over 5 minus 1 over 10 times sine of 2 pi minus, and then substituting 0, the first term would be 0, and then sine of 0 is also 0. Sine of 2 pi is also going to be equal to 0. So right here, this would be 0. And so our solution would be pi over 5. So the area in that one petal of the rose curve is going to be equal to pi over 5. The next example that we have, I'm going to go ahead and circle, and we'll look at this one together in class. The length of a curve with a polar equation, which is r equals f of theta, with theta between a and b, is defined by L equals the integral from a to b of the square root of r squared plus dr d theta squared d theta. And so this formula that we have hopefully looks familiar to what we talked about when we talked about arc length back in chapter 8. So the example right below says to find the exact length of the polar curve r equals 5 to the theta for theta between 0 and 2 pi. So the first thing I notice is for my equation, which is going to be L equals the integral from a to b, the square root of r squared plus dr d theta squared d theta. Since we're talking about the length, is that I know r, however I do not know dr d theta. So finding dr d theta, we need to take the derivative of 5 theta with respect to theta. And so that's going to be 5 to the theta power times ln of 5. And so L is going to become the integral, and we're integrating between 0 and 2 pi, of the square root of r squared, which is 5 to the theta power, plus dr d theta, which is 5 to the theta power, times ln of 5, also being squared, d theta. And so from here, we're going to simplify. We have the integral from 0 to 2 pi of the square root of 5 to the 2 theta, plus the exponent needs to go to both of these. So we're going to have 5 to the 2 theta times ln of 5 squared d theta. And so now from here, there's a 5 to the 2 theta that we can factor out. And so we have the integral from 0 to 2 pi of the square root of 5 to the 2 theta times 1 plus ln of 5 squared d theta. And so you're able to take the square root of each of these factors independently. And so the square root of 5 to the 2 theta, or 5 to the 2 theta to the 1/2 power, is going to become just 5 to the theta. And then we have the square root of 1 plus ln of 5 squared d theta. And note that this part that we have in our square root, and I'll circle that, is just a constant. So since the square root of 1 plus ln of 5 squared is just a constant, we are able to move that out in front of our radical. And so we have just integrating 5 to the theta power d theta. This is going to become in the square root of 1 plus ln of 5, which is just our constant, squared, stays there. And then times, and integrating this, we're going to have 5 to the theta over ln of 5. And evaluating this from theta equals 0 to 2 pi. And so we have quite a bit of constants here. I have the square root of 1 plus ln of 5 squared over ln of 5 times 5 to the theta. And since we're evaluating this from theta equals 0 to 2 pi, that is only going to be on the 5 theta. The rest of that is just a constant, and so I'm able to just move that out in front. So I have the square root of 1 plus ln of 5 squared over ln of 5 times, and we're going to have 5 to the 2 pi minus 5 to the 0 power. And so this is going to simplify to 1 plus ln of 5 squared all over ln of 5 times 5 to the 2 pi minus 1. And this is going to be the length of that polar curve that we had, which was r equals 5 to the theta power, with theta being between 0 and 2 pi.